I rolled a 7. And so I could do the same thing that we're doing here on the board is, start tallying up the data, right? Well, I could pass the dice around. I've done this in class. Pass the dice around. We all roll the dice. Since some of you said you know craps, do you guys know that not all numbers will come up the same when you roll 2 dice? Right? And one of the first things we talk about is we talk about more likely or less likely. Give me a number that is less likely to be rolled than the number 7. Why?
It's harder to get. It's a small number.
Okay, I'm listening. Why?
Because you can't get a 4 with a 5 or 6.
Right. Calvin?
There's less combinations.
Less combinations. Less possibilities. I'm going to stay away from the word combinations because I'm going to reserve that for later. But I know what you mean. There's less ways of rolling a 4 than there are a 7. You see, the big warning I tried to make last time when we're talking about probability and you want to use this formula, right? It's right up here in this part of your notes. The formulas are only valid if all the possibilities are equally likely to occur. That's what we said, right? Well, we can't say that the number of 4s is going to be the same as the number of 7s. Okay? And so I thought I'd show you, how would you compute the probability of rolling a 4, let's say, on the sum of 2 dice? Or the probability of rolling a 7. These probabilities are extremely important. For those of you that do play craps, you know that when you bet on some numbers, it's higher payout if it comes up than if you bet on other numbers. But those numbers are less likely to occur. And let's see why. Now, here's the idea. Suppose I roll 2 fair dice. Okay? When I say fair, what do I mean? I mean each number from 1 to 6 is equally likely to come up. To occur, let's say. Right? So what I want to do now is I want to list all the possibilities, right? I could ask you, here are the possible sums, and here's the probability of y equaling that sum. So I can make a little chart. The sums that we could get, I guess the lowest number would be what? 2. Snake eyes, right? We call that snake eyes. 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. 12 would be the highest, right? Now the probability of these things coming up, that's what I want to show you how to compute. It's not as simple as, it's not 1 out of 12 or 1 out of 11 or anything like that. These are not equally likely to occur. Do you guys know which one is most likely to occur, by the way? Which one? 6 and 8? Now we'll see. 7? We'll see. So here's the idea. The way to do this, I like to represent these things as ordered pairs. Because actually, you'll notice the dice. Oh, maybe you can't tell from the picture. Maybe if I put them both on 6, you could tell. Can you tell that one is slightly darker than the other? But in real life, when you play at the, casino or something, they're not going to have that, right? This is just me getting... What's that?
They do, it's rigged.
I don't know that you know it's rigged.
Because when you put dice into cook them, rig the dice so that it's more likely to...
I did not cook the die. But I will say this, the dice are different. And so what I'm going to do is I'm going to make a little chart
That's where the term cooking the dice comes from. That's the rate thing.
from actually cooking it, huh? That's fantastic. See, I learn more each day. Okay. So what I'm going to do is I'm going to make a little chart. And, okay, we're going to call this one the cooked die, which I never knew I had a cooked die. And this one is going to be the regular one. And what I'll do is I'll just list all the possibilities, right? So 1, 2, 3, 4, 5, or 6, right? And then 1, 2, 3, 4, 5, or 6. So what's interesting here is when I said I rolled a 7, right? It was like this. The cooked die, the darker one, was a 1, and the regular die was a 6. And so one way to represent that, I guess, is I could say, you know, I'm in row 6, column 1. So that ordered pair, 6, 1, represents rolling a 7 this way. Now there's other ways to roll a 7, right? Sure. Let me roll again. Oh, that wasn't a 7, though. I got a 3 and a 5. The cooked die is a 5. The regular die is a 3. So that would represent this one, 3, 5. Right? 3, 5. And actually, if you were to fill in the chart with all the possible ordered pairs, I claim that each of these ordered pairs would be equally likely to occur. Right? How big is my sample space then if I'm going to represent them this way? Yes, 36, right? We have a grid that's 6 by 6, 36. Okay. So I want to do a computation here. I'd like to know, well, so for example, you can now tell me the probability of rolling a 2, right? The only way of rolling a 2 is if you get both dice to be 1s, right? They call that snake eyes. So using our probability formula, what's the probability? It's funny that I see this y. I haven't mentioned that, but I think I will. Y is what is sometimes called a random variable. Random variable. Okay. And when I say here, y is the sum, what's the probability of y equaling 2? A way to write that would be probability that y equals 2. Is that large enough, Amy? Zoom in a little. Okay. I saw a couple squints going on. How's that? So the probability that y equals 2 is equal to what? Use your formula. That's right. That's what we learned last time, right? And from your homework. There's one way out of all 36 possibilities to roll a 2. You guys with me? Let's do the probability of rolling a 4. How could I roll a 4? Might be 2, 2. Here, I'll do this one in blue. Might be 2 and 2. 1, 3. It's interesting because it could be the regular die is a 1 and then the cooked die is a 3. But do you see that it's actually more likely than that? It could be like this, 1 and 3, but you could also get a 3 and a 1, right? So how many ways are there to do it? Here's one, but I could also get 3 and a 1, and that would do the same thing. Does that make sense to people? So what's the probability that y equals 4? What would it be? 3 out of 36, that's right. Am I allowed to simplify that? Sure. If you want to write 1 out of 12, it's 1 out of 12. If you want to use a decimal, that's fine also, right? But you start getting the percentages or the probabilities of each of these to occur. From the chart, can you tell me what the most likely thing to roll is? I don't know. 7? Okay. I'd like to pause and let you guys talk amongst yourself and see if you can compute the probability of rolling a 7. Talk to each other for just a few minutes. Let me list on the chart where all these possibilities are, right? Where are they? You can roll a 6 and a 1, or what else? What else could I roll besides a 6 and a 1? 3 and 4. So that'd be row 3, column 4, be right here. 3, 4. What's that? 2 and 5. What else? Anything else? See, not only could I roll 3 and 4, I could also roll 4 and 3. Do you see that it's going to be all these along the diagonal here? 5 and 2. This will be 1 and 6. So how many possibilities are there? Yeah, 6. So we could say, Calvin, probability that y, oh no, I'm sorry, I'm starting to do here. I was distracted. I won't name the name again. Probability y equals 7 would equal what? Well, yeah. And I remember my father, who loved games and loved mathematics, explaining this to me. He didn't do it this way, though. He didn't say, draw the grid, and 6 out of 36. But what I always thought was really interesting is when you simplify this, what do you get? 1 out of 6. What my dad did was he showed me what a die looks like. I mean, really analyze it. When you look at a die, that's a 1. Do you guys know what number's on the other side? A 6. There's a 5. Do you know what number's on the other side? Yeah, dice are always engineered the same way. Did they have to put them on this way? No, but they put the 6 numbers on this way. I guess the point is, when we were rolling the die, hey, the first die is a 2. Could it be that I rolled a 7? It could be, right? Could it be that I rolled a 2? You already know I didn't, right? Because I would need to get a 1 on both dice. But I don't care what this is. For the other one to be a 7, it is possible, right? So my dad said, when you roll 2 dice, you don't even have to look at the other one. If you see this one, you know what's the probability that I just rolled a 7? It's 1 out of 6. Well, maybe that makes sense to you. I don't know. So I wanted to, get that across. So from the homework, I at least want to go over the 2 even problems you guys worked on. And then if you want to talk about some of the odds, we can also. So 22 to 24, did they have to do with the chapter problem? Was that it? I think so. Yeah. Where we're going to, right. And so this, it says, refer to the sample data in table 4.1 included in the chapter problem. Assume that the subjects included in table 4.1 is randomly selected. All right, so I want to talk about that. The word random, that's the second time we've used it. We talked about a random variable, and here it says randomly selected. So let me go ahead and go back to the notebook for a second here. And let me just give you this definition. When we say randomly selected, when we say that, I guess the word here I'm really getting at is, what does the word random mean? Randomly selected means all possibilities were equally likely. This is, again, the huge idea. equally likely to be selected. Right? All possibilities were equally likely to be selected. So it's not like picking some number between 2 and 12 by rolling dice. That doesn't count. It has to be everything was equally likely. And so what we're looking at here, they say go back to the chapter opener, which I guess, oh yeah, it was page 133, right? Did you guys see this chart? Right? So this problem, they're talking about drug screening. And so it says you may have a positive test result or you may have a negative test result. And it's also true that maybe the subject uses drugs or maybe the subject is not a drug user. Right? So I'm going to go ahead and kind of reproduce that chart for us so that we can look at it. So let's see. The numbers here are 44, and then we had a 90, and then we only had a 6 here. But the biggest number was 860. And I should probably label these so that we can see what's going on. So again, this is, I'll put a plus for a positive test result, and this is a negative test result, right? So this is the drug screening test. And then also, though, we're talking about two different kinds of individuals, right? Here, there are some that the subject uses drugs. And here, the subject does not use drugs. Okay? So, when you're going to do, this is sometimes called a two-way table. The book will call this a two-way table. And when you're going to do some calculating here, I think it's helpful to actually add some things together, right? So I could ask you, how many people in this study do not use drugs? 950, right? You could add those up and you could say, well, 950 of them do not use drugs, right? You could add the columns also. You could say, how many had a positive test? Well, 134. But isn't it true that most of the people that had a positive test actually don't use drugs? Right? We call that a false positive, according to this example. Okay? So yeah, people do drug screenings. I remember having this, certain jobs I had over my life, right? Some places require a drug screening, right, when you get there. And the question is, just because you screen one way, or does that prove? Well, no, there's false positives, and there's also what are called false negatives, right? So how many of the people tested had a false negative?
6.
Right? What does that mean? There's 6 people that do use drugs, but they were not caught, right? Out of how many? Well, out of a lot, right? We have, out of how many?
50.
There were 50 that use drugs. There are 950 that don't. So this is a study where N here equals what? 1,000. And you'll notice one of the reasons it's called a two-way table is if you added these together, you also get 1,000, right? 134 plus 866. Anyways, I think with this information, if you go ahead and fill those pieces in, I think now we're able to probably answer the questions. So let's take a look at the two evens. Number 22 said, find the probability of selecting someone who got a result that is a false positive. Who would suffer from a false positive result and why? So a false positive, right? Number 22, where are we looking at? Which number are we looking at in the chart? I guess that's this, right? Okay. So if I asked you, for number 22, what is the probability of a false positive? You would say it equals what? 90 out of 1,000. Oh, that's a real easy number, right? So what percent is that? Yeah, because it's 9 out of 100, right? So you could say it's 0.09 or 9%, right? So 9% of the time that we administer this drug test, there's a false positive. So the question is, who suffers and why? What do you guys say for this? I mean, the answers aren't in the back.
The person may have a false positive,
Yeah,
and they get turned away.
they might get turned away, right? Amy? Okay. Actually, who misses out? The employee or the employer? Or both, right? I mean, it depends how you look at it. So what should an employer do? Sometimes if you get a positive test, you might administer again. Right? Because, well, we'll see that in a little bit. But if you administer again, there still may be a real low percent chance of a false positive. If you got 2 positive tests, you might start to say, Right? How about 24? 24 asked, find the probability of selecting someone who uses drugs. Is the result close to the probability of 0.134 for a positive test result? How did they get 0.134? Oh, yeah, you could see it, right? What was that? 23 was that? Yeah, so 23 had you compute that. That's what you needed to do. So now 24 says, find the probability that someone uses drugs. What would that be? What number do I want to look at in the study here? Probability that the subject uses drugs. Yep. You can see that it's 50 out of 1,000, or in other words, 5%. So there's a 13.4% chance of the test saying that the person uses drugs, but only a 5% chance that the subject uses drugs. This is where, you may want to look for another test, or you may administer the test more than once. I mean, there's a lot going on here. Okay? Any questions or comments on the problem? Do you guys understand how to handle a two-way table? Where these sums are really going to help you out? Okay? And you could do that on the computer as well for numbers that are a little worse. But this is a nice example, I think. What about other homework questions? Was there anything else you guys wanted me to talk about? You said, I hope he goes over that in class. Yep.
5. It's like,
Number 5?
yeah.
Yeah? Let's take a look. Let's see what it said. Oh, I missed it. It was on this page. Oh, yeah. Identifying probability values. Which of the following are... Oh, I like it. Which of the following are not probabilities? So, Dylan, what were you thinking there?
It's all like ones that are over 100% negative.
Yeah, I mean, you can't have a negative probability, right? So we could rule out negative 0.9, right? No, that's not a probability. Actually, the one before it there. Why can't that be a probability? 7 out of 3? It's greater than 1, right? Greater than 100%. That's what you were talking about.
That makes sense.
Even this, right? 5-to-2 ratio? No. Actually, you'll see this, though. I don't know if any of you are interested in, when they talk about gambling, sometimes they talk about the odds. And you'll see 5-to-2 odds. That means if you bet 5, you might win 7, because the probability is 5 out of 7. But no, that's not a probability. That might be odds. Oh, are you allowed to have a probability? So this one's good, this one's not. Are you allowed to have a probability of 0? You can, right? What's that mean? It's impossible. And then are you allowed to have a probability of 1? That's if something is certain. Okay, that would be probability 1. Okay. Anything else? Yep, Jamie? 29.
Do you feel the probability of one can only occur would be like 1/2 probabilities?
Who says that?
That there's nothing in that is truly certain?
Well, I guess it depends what we're talking about, right? If I go to church, I'm going to hear all things are possible with God, right? This question is beyond my expertise. Let's put it that way. Is there anything that I could say with probability of 1? I'm going to leave it. That's a tough question. But the question was about, the birthday problem. This is classic problem. So, Jamie, what's your question about it? Because there's 4 parts. Okay, let me start with part A. What is the probability that Mike will guess correctly? Well, I guess what we need is we need to understand that we don't have any information. It doesn't say Mike has any information about Kelly. I mean, did he look her up and stalk her for 10 weeks? Or No. We're going to say he has no idea what the birthday is. Right? Yeah?
Can we assume that we already know that certain months are more likely to have a birthday, such as August, September, than, let's say, summer dates?
Is that true?
Yes. August, September, and November are very popular dates.
I feel like it's true in real life.
It is true in real life. Isn't this real life?
You might just say 1 out of 365.
Right. If all the birthdays are equally likely to occur, there are how many days in the year? 365. And so I'm going to guess, if you look in the back of the book, did they say that the answer to part A was 1 out of 365? They did? Okay. So yes. On the other hand, yes, it's a fact that if you go to the hospitals, go to the OBGYN clinic, in the fall, busy season, August, September, October, most popular birthdays in the United States. At least up north. I guess people have nothing else to do in the winter around the holidays, right? No, there's truth to this. There's truth to this. And I look at my kids, they're born August, September. I have October birthday. Right? But I don't think that's what this is going after. I think this is going after 1 out of 365. B, would it be unlikely for him to guess correctly on his first try? Yes. Part C. This is important to understand. Have you ever watched the movie Hitch? You guys see that? This just reminds me of it. If you were Kelly and Mike did guess correctly on his first try, would you believe his claim that he made a lucky guess? Or would you think that he already knew when you were born? Okay. Believe it or not, part C is an extremely important question.
Based on the data, I would think that he did.
You would think he knew. Why?
Because there's a 1 out of 365 chance that,
Yeah.
you know.
So his chances of guessing right were only what percent? Let's get a percent. Right? Because, I'm just better with percents than fractions in turn. Oh, so what was the chances of him getting it right? Less than 1%, right? 0.002, we're talking, 0.0027. Significantly less than 1%, less than 0.5% chance. And he guesses it right on the first try. What's Kelly going to think? Stalker. No, Kelly might be suspicious. And I want you to understand something. We are going to be suspicious also. You guys, if I roll the dice and I get You can't see it. I'm sorry, it's off the screen.
Let me know correctly.
There. I rolled snake eyes, right? Would you be surprised? Here. Let me roll them again. I'm sorry, you can't see it. Let me put it on the screen. Ah, I rolled it again. Would you be surprised? Here, let me roll it again. What would you start to suspect after I rolled it 3 times in a row? I've been cooking the dice. That's the point of this problem. Not this one. Where is it at? This one. The point of the problem is, if you see something very unlikely to occur, sometimes we're going to say, wait a minute. Maybe my original assumption was false. Yeah, part D is just for fun. That has nothing to do with any mathematics. But part C has everything to do with mathematics. You guys, it's going to happen. I told you guys, real statistics is beginning around chapter 7. And in chapter 7 and chapter 8, we're going to be testing assumptions. And if we get something that's really unlikely to occur, and it happens, we might say, wait a minute. I don't think you randomly guessed my birthday. I think you're stalking me. This is a very important idea that the book is communicating here. So I'm glad you asked that question. It's good to have on the video for people that weren't here today, for instance. Okay. All right. What's called the addition rule for probability. So, here, a little bit too close now. Zoom out a little bit. Okay. So this is section 4.3. And it's called the addition rule. And section 4.3 and section 4.4 have to do with when you're talking about more than one event occurring. Okay? So the rule is this. It's for when you want to find the probability of A or B occurring. The probability of A or B. And the rule is that the probability of A or B is equal to the probability of A, you can probably guess what I'm about to write, plus, what? The probability of B. Unfortunately, life is not that simple. I wish that were the rule. But there's more to it. You need to subtract something as well. You need to subtract the probability of A and B occurring. And I'm going to see if I can help you make sense of that. Matter of fact, I think I'd like to go to that example we were just looking at with the drug testing. You know? Let me try and use the formula. So let's suppose we want to, I'm going to do this. I'm going to let D, let this represent, so how about I write it this way? Let D be the event that the tested subject uses drugs. I'm pretty sure on the homework you guys computed for me the probability of D, right? We should look at that chart again. That'll help. Here. If I want the probability of D, here's the table. So let's see. What would be the probability that the subject uses drugs? 5%. We did that already. So the probability of D is 5%. Okay. Now I could do this. I could say, let C be the event that the test gives a positive result. I don't know if we computed that yet, so let me go ahead and compute the probability of C occurring. Where would I be looking? Oh, yeah. Oh, we did that in problem 23. The probability of C occurring, that was 134 out of 1,000, so wasn't it 0.134? You guys with me? So what I might want to do now is I might want to compute. The addition rule is used when you want to compute the probability of, let's say, C or D. Or is the key word here. That signifies additional. So what happens? It's the probability of C plus the probability of D, but then you need to subtract the probability of C and D occurring. I'm sorry, these should be capital, because they're events. So let's write out what that is. Right? Well, what's the probability of C occurring? It's 0.134. What's the probability of D occurring? It's 0.05. But we also need to subtract what does this mean? The probability of C and D occurring. What would that mean to us? Yeah. So two things happen. What has to happen? They test positive and they use drugs. Where is that in the chart? 44 out of 1,000, right? And so what we need to do to get the correct answer here is we need to subtract, I guess it would be 0.044. And that will get me the right answer. Okay? And so I think you get, I have to work it out, but I think you get 14%. Is that right? Let's see. 0.139. So yeah, it would be 0.09. So there's a 9% chance we could say. Here, let me just make sure I have that right on the calculator, guys. Can't hurt to double check. We have the technology. Let's use it. So what are we doing? We're doing 0.134 plus 0.05. But we have to subtract what? 0.09. No. Subtract. I had it. 0.134 plus 0.05, but now minus 0.044. And so I'm getting, I didn't add right. 14%. Okay, I'm glad I double checked. Oh, right, because it was 18.5 under that, so 0.14 would be the probability, 14%. Why do I need to do this extra subtracting? One of the nicest ways to explain it is what's called a Venn diagram. You guys know what that is? You guys know what the MasterCard logo looks like? To me, that's the Venn diagram, right? So here's the deal. If this blue circle represents event C, and if this green circle represents event D, let's say, when you count up C and D, there's a problem. if you add the probabilities of C and the probability of D, the problem is that you counted this twice. So that's why we need to subtract off, this is what is C and D. It's also called the intersection of the two sets. But you need to subtract that probability. So I guess looking at the chart that we had, you know, if I want to compute the probability of C or D, I have 134 that were positive drug tests. I have 50 that are actual users. But if I just use those numbers, I double counted these 44, right? So that's why we subtract that off. Does that make sense? No? Let me put it this way. How many people here in this study use drugs? Well, 50, right? There's 44 of them that test positive and 6 that test negative. That's 50. You guys with me? How many of them got a positive drug test? How many of the 1,000? Well, 134. 90 of them do not use drugs and 44 of them do use drugs, right? So here's the problem. If you start adding 134 and the 50, you're going to think the answer, that's where these came from, is 0.184. But that would be wrong. Why is it wrong? Because then we counted the 44 twice, once in this row and once in that column. So we have to subtract it off to get the right answer. And if you follow that, then you understand the addition rule. As written up above with A's and B's, or you could write it with C's and D's, whatever. But that's the addition rule. Again, the key word is if you're in what kind of a situation? Or. An or situation tells you you're going to have the addition rule. Now, I want to give you a little bit of information about the multiplication rule. Let's look at that. And then tomorrow when we come to class, I have a group work plan for you guys where we're going to be working on both of these ideas significantly. Okay, so here we go. Section 4.4. Okay, this is the multiplication rule. And so this section talks about how to compute the probability of A and B occurring. The probability of A and B occurring. So, here I go. It equals the probability of A. You could probably guess what I'm about to write next. Times, because it's called the multiplication rule. And you know what I wish I could write? I wish I could write the probability of B. That's not quite true. Almost. What is true is that we can write the probability of B, and this is how you write it. You put a bar, a vertical bar, and the way you read that symbol, this symbol here means the probability of B given that A occurred. So let me see if I can come up with an easy example for you. How about this? I have 4 coins in my pocket. 4 coins in my pocket. What are they? They are a quarter, dime, nickel, and penny. So let me say this. I randomly select 1 coin from my pocket. Okay? So I could ask you, what's the probability of selecting, which one do you want? Let's say the dime. What would you say? 1 out of 4. Why? Well, when it says random, what does that mean again? Everything is equally likely. Now you could argue, hey, Paul, the dime's the smallest one, right? But no. We're saying they're equally likely to occur. And if that's true, then 1 out of 4. Okay? Now, maybe I should have done this. I should have said D is the event selecting the dime. How about this? Q is going to be the probability of selecting a quarter. Okay? Selecting a quarter. So what would be the probability of Q? Well, it's also 1 out of 4, right? It's just as likely as the dime because we said the word is random. But now, what if I said, what is the probability of first selecting a dime, then selecting a quarter from the remaining coins? So here's where things are a little bit different, right? And that's the idea that we're trying to get across here. The probability of B given that A already occurred. Okay? When I say selecting a quarter from the remaining coins, right? This is where what I'm writing is probability of Q, and I put that symbol, given that D already occurred. That's what we mean. And what would that be? The probability of Q given that D already occurred? 1 out of 3. Because there's only 3 coins left. Does that make sense to you guys? So this symbol that we have to use with the multiplication rule is saying you need to take into account what already happened when you use the multiplication rule. Okay? And we'll have some more examples of that tomorrow, actually. think I want to pause because I want to go to the back to the experiments we were doing. We did experiment on the board over here. And I'd like to go to, those of you that have the ebook have something called StatCrunch, and it has a really nice simulation for die rolling that I'd like to show you guys and share with you. I think this would be maybe a good way to finish up here in the last few minutes of class. We'll come back to these rules tomorrow. So let me go to StatCrunch. And that's right here maybe. Well, no, I got to go back to the website. StatCrunch. StatCrunch is a lot like Excel. Not everyone has it, so guys, I guess we're just going to do a little watching. You may have taken some notes, I'm not sure. So let me go to the StatCrunch website. Oh, but you do have on Excel, you guys have some of this data, right? Was anyone able to compute the mean or something like that? That's not what I want. I just want StatCrunch running. Thought I had it. Here we go. Okay, that's good, but what I really want, when you load StatCrunch, again, these are all the different data that came with the book, but I'm going to click on this applet, and here I have simulations, and you'll notice we have coin flipping, dice rolling, etc. Let's do some dice rolling. Okay? So it says simulate a sum of dice. Number of sides on dice, 6. You could change that, right? We know there's dice that are different shapes. Number of dice to roll. Let's just roll 1 for now. Tally the roll results. Okay. Let me compute. And so, it says how many times do you want to roll the die? Well, let me roll 1. Hey, I got a 3. And so it shows me a 3. Let me roll again. I rolled a 4. So this can roll dice. Right now, this is no faster, right? But I could do 5 rolls very quickly, and it doesn't have to show me every time. It'll just drop them on for me. Right? And I mentioned last time this thing called the law of large numbers. Do you guys remember what that says? It's in our notes. Let me pull it back up. Similar to what? It says, yeah, they will approach the classical probability. Now, my question is, guys, what's the probability of rolling a 5? We did that with 1 die. We said it was 1 out of 6, right? That's because when you roll 1 die, all the results are equally likely to occur. Actually, look. If you just looked at this data, see how we rolled a 5 twice? I would say, oh, okay. So maybe that happened more often. But notice what you could do here. You could do 1,000 runs. That's a lot faster than us passing the cup around in the classroom, right? And so you can say from this, hey, what's the probability that the sum is greater than or equal to 3.5? And that's this in red here. It says 49% of the time it was greater than 3.5. I can change this. I can ask, what's the probability that the sum equals 5? And it says 0.16. Is that a pretty good approximation to what the answer should be? What should the answer be? Well, we can come here, right? We could say, what should the answer be? The answer should be 1 out of 6. This is what classical probability predicts. 0.166, right? What the law of large numbers says is this. If you repeat the experiment many times, here, let me do another 1,000 runs. This number is going to get closer to 0.166. Let me run another 1,000. You guys see that? Okay. Let's get rid of that and try 2 dice. So I think this is important to see. So again, I'm going to do another simulation of die rolling. The difference is, this time I'd like to roll 2 dice. By the way, what was the most likely number to occur when we did 2 dice? We computed it. 7. Least likely? 2 or 12, right? So let's compute this. Now again, if you just roll it 5 times, okay, we rolled a couple of 4s and an 8 and a 10 and an 11. I'm going to do another 5. By the way, I just got introduced to this new game. Have any of you played it called Catan? The Island of Catan or something like that? No? It's a board game that's real popular, and I was really disappointed because I needed 8s to be rolled, and they weren't rolling 8s, right? Kind of like here, we're not rolling 6s, it looks like. But if we do 1,000 die rolls, well, now it's a little different, right? Hey, remember we computed the probability of rolling a 7? Let me make this an equal. What's the probability of rolling a 7? Again, it should be 1 out of 6. Are we getting close? We're getting close now, right? Let me do another 1,000. We're getting even closer. Should be at 0.166. Sometimes it's a little above 0.166, sometimes it's a little below. But if you keep doing thousands and thousands of die rolls, you're going to get closer to what is predicted by classical probability. And by the way, you guys know the word for this, right? What distribution are we starting to approach when we do a sum of 2 dice? The normal distribution. Classical probability would predict that that would happen. That's chapter 5. I don't know how much of that we'll do. But I thought that this might be good for you to see. So, I guess we didn't get that far with the thumbtacks, right? Did we get far enough to convince you that these numbers that could come up are not all equally likely to occur? Did we get far enough for you to be convinced that there's a difference between the thumbtack problem and the die roll problem? What's the difference? Mm-hmm. Well, I guess you have more, though, the way we did it here. Like, I could ask how many thumbtacks came up, right? But I see what you're saying, because when you do a thumbtack, it's either up or down. Let me ask you guys this. Do you think flipping a thumbtack, it's equally likely to be up or down? Looking at our data, is it more likely to be up or down? Looking at our data. It seems like it's more likely to be up, because we had 6 people that had 6 of them up. Can you give me a reason why that might be true? Weight of the surface, right? If it's just on the edge, right? I mean, and this is what's usually done in statistics. We look at data to base our reasoning, you know? So I kind of like that experiment as well. Hey, it was a quiet day today. Tomorrow's a little different. Tomorrow you come in, you're getting to work on some group work, okay? So we'll see how that all goes. Have a good day, and I'll see you tomorrow. Stop by if you want extra help. I'll be here all day.